Good morning, good afternoon, or good evening, depending where you are in the world, and welcome to today's Design News webinar, Integrated Actuators Made Simple with Python, sponsored by Harmonic Drive and broadcast by Informa. I'm Michael Krieger, and I'll be your moderator today. We have just a few announcements before we begin. First of all, this webinar is designed to be interactive. On the right-hand side of your screen, you'll find the Navigation Center, which will allow you to learn about our speaker, download resources, and participate in the Q&A session that takes place at the end of the presentation. If you experience any technical difficulties, refresh your webinar console within your browser window. That's usually as easy as hitting F5, or type your issue into the Q&A area, and we'll be glad to offer one-on-one assistance. And lastly, before you leave us today, please complete our webinar survey, as your feedback will provide us with valuable information on how we can make these events better for you. Now on to the presentation. Discussing today's topic is Marcel Almonte, Mechatronics Application Engineer at Harmonic Drive. And to learn more about Marcel, just visit the Info tab in your Navigation Center. Marcel, thanks for joining, and over to you.
Thank you, Michael. So I figured we'd start off today talking about integrated actuators made simple with Python. Before we get into the weeds, I'm going to tell you what an integrated actuator is. So in a general sense, in a conventional system, you'll have a brushless DC motor paired with the servo drive and an encoder. What makes it a servo system is having an encoder feedback to close the loop on your position. In general, you would need multiple cables for feedback and power and any other sensors that are going to be plugged into the servo drive. What makes this technology unique is these are all combined into one cable or a separate cable for different types of communications on our EtherCAT units. As you can see here, there's a wide range of product lineups, with our smallest being the RSF3 on the right and our largest being the SHA32. These have integrated servo drives on them, and we'll get into the weeds on what that actually means. So this is kind of a layout of our products and what they offer. In general, we have two flavors of communication. We have CANopen and EtherCAT variants. The SHA series and the LPA offer EtherCAT and CANopen. In today's webinar, we're going to be focusing on CANopen with the FHA Mini. A few things I want you guys to note on the side is these are designed for DC bus voltages ranging from 24 volts to 60 volts DC. And depending on what you have available, you can use different voltages within these ranges. In general, CANopen is the core element for these types of communication. And so long story short, even for EtherCAT communications, the same fundamentals apply with CANopen. So being able to grasp and understand what's going on at the actuator level really clarifies if you want to jump into a faster protocol like EtherCAT. In a general sense, the idea is using a CAN bus. And so you may ask, well, what is a CAN bus? So CAN stands for Controller Area Network. In a general sense, you'll have two CAN wires that are typically twisted together. In order for these to know what the connection is, there's a termination resistor in place. This diagram shows here what a CAN bus wiring would look like, and it's a physical connection. And essentially what's happening is it's sending bit by bit. And how it's doing that is it's pulling the voltage down and looking at the differential between the two lines to say, okay, is this a 1 or a 0? But the beautiful thing about CAN bus is it's able to look at that differential. So if you have any, say, voltages or spikes or other EMI or other situations where there's going to be noise, it's not just looking at the raw voltage, it's looking at the difference between the two high and low signals. And one other thing I want to mention with CAN bus is there's a level of bus arbitration, with the idea being the higher node ID, or in this case, the lower one, for example, node 1, is going to take priority on the bus over a higher node. So for example, when you're setting up a system, if you want node 1 to be your most important access, you can set that as a lower node versus your higher nodes, such as like 2, 3, up to 127, can take lower priority. In a general sense, CAN bus has been found through many different types of technologies, and it's a physical wiring even used back in the 60s, 70s, and 80s just to wire up things like, say, your garbage truck or an automotive. And so in this case, we're using what's called CANopen. And so you may ask, well, what is CANopen? So essentially, CANopen is a higher level protocol built on top of CAN bus. It has a few standardized concepts. So if I was just going to use a CAN bus, I'm going to have to develop custom messaging and arbitration for those vendor-specific things. CANopen adds a standard of that. Specifically, it adds the ability to have object dictionaries. So these are existing parameter mappings on what different types of objects are going to be used. It adds things like NMT, which is for network management. It allows for PDOs, which are essentially process data that's run cyclically, and SDOs, which are essentially your set and getters. And the idea of using CANopen is it allows for interoperability between different devices, and it has base level device profiles like the DS402 device profile. So a few key concepts here are master and slave, essentially having a master node say, I want you to follow this position. Also client and server being able to publish states saying, I am at the operation enable state, and things like producer and consumer being able to say, hey, everything is all set. So say, for example, you have a heartbeat that's pushing out, hey, I'm alive, keep going, everything's good. And in general sense, it's kind of split between, having your network that's running and saying, is the network in okay state? Then having your device specific profile saying, I'm a device with these types of objects and I'm designed to do X. So when it comes down to the raw level of CAN bus messaging, I wanted to kind of get into the weeds about what CAN bus messaging looks like. So in a general sense, there is what's called the COB ID. A COB ID is a mix between what node and the function code. And this function code, which I'll show in the next slide, depends on the type of message. And this is how the CAN bus can differentiate between node 1, 2, 3, and what it wants to do with that. COB IDs are fixed and they change depending on what node is doing what. In a general sense, you're going to have your arbitration field, which is going to tell you, hey, this is what node I want you to access to do what. You're going to then say, I have a control field, which is going to say, here's how much data is in there. And one really important thing is the CRC field. So essentially, it's a cyclic redundancy check, and it adds up all of the bits and then says, hey, does this checksum match? This is really important for maintaining consistent messaging and seeing if there's any noise or error on the actual bus itself. So the CRC is essentially a last check that says, hey, I am in a good state. I got this message. All the information in here stacks up for what it should be. So in a general sense, there are a few concepts I'm going to cover in this example. We have service data objects, which are your setters, your getters, configuration level stuff. This is going to set your limits. It's going to be used to set parameter values, and it's really used on startup. And over here on the right side, you're going to see an example of different COB IDs. So these different COB IDs are used to access different types of data objects. For example, the lowest level is the emergency. This is going to say, hey, are we in any error states? Did we have a bus overflow? And kind of give you general, hey, is my network okay? Also, you have different data objects for SDOs, which are kind of doing like a handshake. Essentially, they're saying, hey, I would like to write to this object. It'll receive an acknowledge back saying you're okay to write, and then it'll write to that. Process data objects, they are enabled in the pre-operational to operational state, where you've essentially mapped out where this data is going between the main device and the slave device. So instead of having the overhead for like an SDO, where it says, I want to go to this node with this function code for an SDO, for this index, with this subindex, with this data linked, this is already mapped out between them. So essentially, it compresses the amount of overhead and allows you to put more data into a single frame. In a general example, you have a few different things with the CANopen device. You have an SDO server, which is going to be setting and getting parameters. You have the object dictionary, which is going to be hosting those parameters. And these are going to determine like what parameters can be written to, what parameters can be mapped to process data objects, and what type of information they are. Is this a record? Is this an int? And so on. And in a general sense, process data is happening cyclically. And this is important because if you want to, say, pull the position off of, say, an actuator, you want to get that position quickly and in real time. And having the full overhead of an SDO is going to delay that process. So process data objects really get that real-time performance. And these same concepts also apply with EtherCAT. So being able to understand this in the CAN bus level also helps you start to understand on the industrial Ethernet level. So what I'm going to highlight now is what topics we're going to cover in the next section. I'm going to show a little plug and play example and go over the code repo from the README to how to install certain pieces, what hardware you're going to need, and so on. In that example, I am going to be using an FHA Mini size 8, the 100 ratio, and it has the I/O option. So you're going to need a few things for that. You're going to need a USB to CAN adapter. In this case, I'll be using a PEEK. You also need the proper cables, a termination resistor. This is really important because the CAN bus is electrically terminated with that termination resistor. If you don't have that termination resistor, your nodes aren't going to appear and you're not going to be able to see any traffic. And the last thing, you're also going to need unique node IDs. In this case, we're just going to leave it at node 1, but in a general sense, you can support up to 127 nodes. And after going over the hardware setup, we're going to step into fundamentals, the DS301, DS402, a little more about service data objects and process data objects. Then I'm going to show the GUI example on how to write to the state machine and make some motion. So that's what we're going to be talking about in this next section here. I figured I'd highlight it before we get into it. README page. First thing you're going to notice when landing here is there's these links at the top. This one will point to the Harmonic Drive GitHub, our website, LinkedIn, the integrated actuator page, and the YouTube page for any other relevant product content. So to start off, this repo is used to plug and play with the HD LLC integrated actuator product lineup for CANopen. It leverages the Python CANopen package to create motion with the DS402 state machine and protocol. In a general sense, it's split off into two sections. The first section will be going over the prerequisites, installation, CANopen fundamentals, and the next section will go more into the script structure and making motion. One thing I want to highlight is there is some setup you will have to do. The first thing I want to mention is you're going to want to make sure you have an actuator in hand. You want to have a USB to CAN adapter. I recommend PEEK or Kvaser. Typically, the PEEK is my personal go-to. I have one right here. So this is a PEEK adapter. Just to show it here. It has a termination resistor, a DB9 termination resistor with 120 ohms resistance, and this is used to electronically terminate the bus. And essentially, you're going to need these termination resistors either at the end of your buses or if you're doing kind of a single loop right at the end of this connector here. This is what you're going to use to talk and communicate with the actuator. That's one element of it. Another thing you're going to need is a interface to the integrated actuator itself. In this case, we have a LEMO connector that features CAN signals and power. In this case, I have a little jumper here for 24 volts. So that's what's going to be in terms of hardware needed. If you do go with the PEEK option, you're going to want to install the relevant drivers as well so that it's recognized in this suite of code here. One thing to mention is you're going to need an EDS file. Essentially, an EDS file is an electronic data sheet that lists out all the objects, what access they have, and if they're process data object mappable and other good stuff like that. Essentially, this is the data sheet used to set up a device in a CANopen network. In this case, we are using the FHA Mini, so that's the data sheet I'm going to be using today. So as far as hardware setups, just to go over real quick, CAN interface, termination resistor, Python installed, pip installed the CANopen library. There's a link at the bottom of the README if you're curious what the library is, built off an existing code repo. And then you're going to need to place the EDS file that you use in the EDS folder here. So once you've installed all that, you'll be ready to start making motion, assuming you have an actuator and power. So. Specifically, the DS301 state machine and the DS301 implementation is going to determine what parameters it can communicate with, what process data objects are mapped out to, and it's going to set up your machine to be ready to communicate with other devices on the network. One thing to mention is that in order for these devices to communicate, they also need to have the proper bus termination. Otherwise, you're not going to recognize anything. In addition to that, each device needs a unique node ID to start up. In the pre-operational state, that's where your service data object, your SDO communication is going to take place. Essentially, service data object communication has the full address of where it wants to go. It's going to tell you, I want this node with this function for this index and or this subindex with this data. It's very explicit in how it's written, and it's used to kind of set and get various parameters on the device. Once the device is in the pre-operational state and everything checks out, it's going to then transition to the operational state. In the case of the operational state, this is where your process data, your cyclic data exchange is going to take place. Essentially, process data objects don't have the same overhead as an SDO. The mappings have already been configured between the main device and the sub-device, or the master and the slave. And the idea is to send the raw data on the network, and depending on what type of process data object receive or transmit, it'll determine who should listen and who should do what. In the case of transmit process data objects, those are usually what's coming up from your slave device, in this case, the integrated actuator, and they're being sent up to your main controller. And then your receive process data objects are coming down from your main controller, and they're writing specific process data values to the device. Typically, in this case, you would have a status word that would come up from the node and say, hey, this is my current state. And then you'd have a control word come down from the controller and say, which in the case of the master, say, all right, do this. This next portion, I'm going to go over holistically these two state machines in action. Essentially, we have the DS402 state machine that's operating on the device, and the DS301 that's acting as the network management layer. Specifically, the DS402 state machine is for servo drives, and there's common objects in those. I'm going to keep this fairly straightforward. Right here, this is the DS402 state machine. Essentially, there are certain bits in the control word and the status word that are used to represent different types of states and information. In a general sense, the control word is coming down to control the state machine, and the status word is going out saying, here I am. These are the list of different state transitions with the relevant bits. In this case, we have our general transitions here and control word specific bits and the status word bits. The standard object I was talking about before, here's a list of a few of them: target position, target velocity, target torque, position actual value, torque actual value, velocity actual value, to list a few. Another thing with this, there is a mode of operation and mode of operation display. These are used to determine what mode of operation the device is currently at, and as well as setting it. The display is used to say, here is the current mode of operation, and then the 6060 is used to set that mode of operation. Want to go back, take a few steps back, talk about CAN communication as a whole. Before getting hands-on. In general, there are two types of communication. We have our service data objects, which are kind of your sets and gets, and then your process data that's happening cyclically. In a general sense, this is a brief example right here, where if I wanted to set an object value, this is what I could do to set it via SDO versus PDOs. I'm directly writing those mappings. Right here, these are the default mappings of PDOs for the integrated actuator lineup. So those are useful for getting your device set up for using process data objects. You're going to need to know what these are, as well as be able to understand how many you can fit into a PDO. We can go over those details in a more advanced setup. In a general sense, from the code repo, you have the ability to print them all out. This is how you can map a different one, essentially reading what the process are, clearing them, adding them, and then setting your transmission type, whether it's I want it to be every sync, It's kind of think of like a metronome where do I want it to be on every beat? Do I want it to be on every 2 beats, 3 beats, 4 beats, 200 beats? And then eventually, do I want it to, for asynchronous type communication, do I want it to update every time it changes? And those are just kind of a general overview of these, but they'll make more sense once we make some motion here. So after we've explained some of the basic communications, what I'm going to do is step into the GUI. I'm going to plug in the FHA Mini and show you guys these concepts in action to make more sense of them. It's something you kind of have to see a few times before it starts to stick. So I'll show you with this GUI. This GUI example will be available on the GitHub. So if you're looking to essentially grab it, build off of it, or just use it as a first round pass, that's a good starting point for it. Here we have the FHA Mini IDT size 8. We have 2 LIMO connectors on the back and an indicator light right here. This is our I/O connector, and this is our power and CAN connector. So what we're going to do is we're going to grab a LIMO, a power and CAN cable. We're going to plug that right in there. The next step is we're going to take our DB9 connector, plug it into the termination resistor, which is connected to the peak adapter. So we're going to connect this here. After that, we're going to connect our power. So before we plug the AC line in, going to connect here, and then we're going to connect to our adapter for our 24 volts. So now that we have power on our device, this can be shown by the indicator light right here, we are then able to plug this into our computer. And this is essentially the short and quick. Here's how you wire up an FHA Mini with an integrated set. All right, now that we have officially wired up the FHA Mini and have our peak adapter plugged in, what we're going to do is open up the GUI example. In this case, we found right in this GUI example folder right here. So we're going to take this, and then we can run this script here. So first thing that's going to pop up is this GUI window right here, and you're going to see that the connect to actuator button is blinking. So we're going to click that. And this is going to allow us to connect to our device. What we're going to do is make sure we have the correct EDS file mapped out through this browser right here. So I'm going to add that. One important thing that I forgot to mention earlier is not only do you need to have power, terminated CAN signals, you also need to have the correct bit rate, which in this case, it's 1 kilobit per second. So now that I've added my path, I'm going to click the connect button. Can indicate that I'm connected. Once I'm done with that, I can close this window here. What we can see now is our device is in the switch on or ready to switch on state. Right here is the essentially control word state machine walkthrough. So what this specific GUI interface is used for is to walk new users through the CANopen state machine. So what's going to happen here, it's going to suggest I transition from ready to switch on to switched on. And this is the specific hex value that's being written to the control word. So we click this, we're switched on, and then one more will allow us to get to operation enabled. So once we are in operation enabled, there's one more thing we want to make sure. We want to make sure that we have a mode of operation. In this case, when you select the drop down, it's going to set that mode of operation for you. The default it's going to set to, in this case, is profile velocity. One thing it's also going to show is the gear ratio, as well as the position in counts and in degrees of the output. So that's just a quick tangible way to see where your actuator currently sits. One thing we're going to do next is we're going to click the show plot button. This is then going to appear with the plot, which is going to track our position, our velocity, and our actuator current. So if we want to make some motion, all we have to do is drag the slider. So we are going to drag the slider. This is going to create some motion. You can see right here for FHA 8. The slider is a useful way to test out different velocities and speed, change direction,
get a feel for velocity control. We also have the option to write zero velocity, essentially stopping the device. And not only this, we also have the ability to set our acceleration and deceleration. Both of these are in terms of motor RPM. So if you want to define it in terms of RPM of the output, you're going to need to essentially calculate the gear ratio in that factor as well. Now, if we wanted to change our modes to profile position mode, one thing I'm going to show real quick here is first we're going to go to homing mode. And then we're going to use method 35, which is going to set our current position as our home position. So essentially we're going to write that. Now we see our actual position value is updated to 0. This is stored in the position actual object. We then want to go to profile position mode. We have a few different options here. We have our profile velocity that we're going to set. In this case, I'm going to set this down to 2000, enter set. And then we also have the ability to adjust our target position. In this case, I'm going to make it something like 100,000, set this, and then we have an option to move absolute or relative. With a relative move, it's going to take that target position value, which is the one that I wrote up here, and it's going to either add or subtract from the current position the actuator's at. Depending on if the target position value is negative, it'll go one direction, positive go the other direction. So if we were doing a brief relative move, you can see here on our plots on the side, making some relative motion. We can then go back to making an absolute move. If I put this to 0 and set it, and I can make an absolute move all the way back to 0. So that's kind of the idea with profile position mode is essentially you're writing a value to the target position. You're then in the control word, you want to determine if it's relative or absolute. And then once you send that command for relative or absolute, you're also changing the set point bit. We can go into more details in the actual script, but that's essentially what it's doing here. In addition to this, we have a few other features for this GUI example. In this case right here, I just opened what's called the object browser. This allows you to scroll through all the parameters in the object dictionary to monitor them, as well as if you wanted to write to them. So for example, if I added the actual current, I can add a monitor, and this is going to be pulling them via SDO. So more of a, hey, I want this value, okay, send back. And then you also have the option here to write to different SDO objects. This can be useful for setting different modes of operation during initial testing, setting limits, different types of parameters, stuff that normally wouldn't be handled by process data objects. And that's kind of the short and sweet of it. You can add multiple objects to this monitor, and it's good to say, for example, if you were doing some initial tuning or setup, you may want to add, say, a position error value, all that good stuff. Essentially, this is a direct access to the object dictionary, which was populated from the EDS file. So I restored the plot feature here, and I wanted to show you some different state machine transitions. You have the ability to do fault reset, quick stop, recovered operation enable. In this case, I'm going to do a fault reset. It's going to send that via the control word. This is useful from a top-down approach. Hey, I had a fault or an error. The next thing you're going to do is if your device is in a faulted state, you're going to look at the drive and status flags. So we can open that by clicking the view drive and status flags right here. I'm going to hide the plot real quick. This drives and status flags object 200D gives us a little more information than the status word does. The status word may indicate that we are in a faulted state. The drive flag or drive status flags is going to tell us what type of faulted state. Specifically, do we have an I squared T where we exceeded too much current in a short period of time? Is it a following window error, such as a velocity window error or position window error? Is it a situation where we had lost power and the drive had gone under voltage? These all can be seen inside of this 200D. And this is kind of the next level for troubleshooting and setup. If you want to get into the nitty gritty, one thing you can go to is using the PCAN view. Specifically, this pecan view software is useful for understanding what type of data is being transmitted. And if you're ever needing to essentially capture an error event, you could go to this trace file here, record the network traffic, and then this can be used to help understand what is going on in my bus. Am I using all of it? Am I sending multiple of the same messages repeatedly, flooding the bus? And this is kind of a last level sanity check for communications, especially before you go and implement it into a larger, more real-time controller, being able to troubleshoot something like this in terms of Python for slower speed stuff, and then iron out a lot of the details. So when you get to your full controller, you have a rough idea of what the communication should look like. So now that we have went through the GUI example, I'm going to give a quick overview of the script structure. Essentially, what we're going to do is do network is equal to CANopen.network. This is going to create our network, and then we're going to use the network.connect. Afterwards, we are going to put our interface here. In the example before, we used pecan, but a lot of these interfaces are listed in the original CANopen package and what's supported. After we have connected to our say USB adapter, in this case it would be the peak for the setup that we have here, we are going to add the node. In this case, we're saying, hey, I want this to be node 1. Here's the ES file. Let's add it to our network. Afterwards, we're going to start with the clean slate in terms of network management, reset the communication. Then we're going to start our sync cycle. This is going to essentially keep the pacing of our network. Afterwards, we're going to load up our process data object configuration and also load up the setup state machine. This is going to use those process data object mappings for the control word and status word so that these state transitions below work out the box. And that kind of covers initial setup. What I'm going to show you now is how that works with a profile position mode script. So now we're going to open up our profile position mode script. This will be under motion examples, under single axis, under profile position. We have a few different options here. We have PDOs and SDOs. First, we're going to start off with SDOs, and then we're going to go into PDOs. So let's start off by opening the SDO script. So at the top right here, we're doing all our imports. These are mainly used for helper functions, waiting for homing, homing on the current position, decoding any faults, writing, all that good stuff. Right here is where we actually get into what I was mentioning before, where we're going to create our CANopen network, add our interface. Then we're going to add our node in with its ADS file. We're then going to reset our connection. We're then going to start our sync cycle, load up our process data objects state machine, read off the vendor ID and device name via SDO. This right here shows where it's accessing a subindex on the specific line versus this is just accessing the one object that's in there. We're then going to put our device into the operation enabled state. We're going to transition through our state machine, make sure we're all set on the status word, home. Then we're going to set our mode of operation and profile position. This is more of a sanity check to walk through the state machine. And then here's where our actual control loop starts. We're essentially going to write our target position via SDOs in this index right here. Every time we have a new target position, we're going to cycle our control word for a new set point. This is just bringing it back to, which is essentially it's bit 4. So we're saying, all right, go. Bring bit 4 back to low. And then every time this loop repeats, it's going to rewrite that new set point. Here, we're going to pull our position and velocity and print that out. And then at any given point in time, we can press Control-C on the keyboard to stop. And then once we're all set, we're going to disconnect and put our device into the pre-operational state. All right, we're now going to run our script. Here we're making a few different moves. This is for slower control. PDOs are definitely the faster option here, but all the same communication and controls can be done with SDOs. So the main idea behind this is to test basic communication. Can I write to these objects? Can I make motion before jumping into the process data objects? So this is kind of just a brief example where you can see the FHA mini on the left right here, going through all these different positions. These positions are represented in terms of motor counts. So that amount of counts depends on the encoder resolution. The next example I'm going to show is the profile position move with process data objects, specifically creating a sine wave. So all of the setup is pretty much the same. The main thing here is we're creating a bunch of different sine wave points. So the idea is the user would put in how many points they would like to use. For example, 20,000 is the amplitude at 1 hertz, 50 samples per second for 1 minute, essentially. This takes us in, is going to generate that an array of points. Once that starts, it's going to go through. This is an example of writing to the control word. This does a fault reset and then walks through the operation enabled state. Afterwards, it goes through, it cycles through those points that were generated in this function right here for generate sine wave. So we're going to go ahead and run this, and that'll show an example. So and this is very, very small, but the idea is you have a sine wave that's moving. For profile position move using process data objects. So this would be useful for tuning an external controller. Say you want something to, you want to see how the system reacts under different types of loads and inertia. This sine wave can be useful for that initial single axis setup. So the idea is you can grab this, tweak it, and use it as a first round. All right, let's make some sine wave motion and see how it performs. You're obviously going to get better results with a industrial real-time controller, but this can help get from bench top to the next level. So now that we've covered profile position mode with process data objects and service data objects, going to show you cyclic synchronous position mode. So essentially, cyclic synchronous, the main difference is instead of cycling the set point bit in the control word every time, you're going to leave that high, and you're going to dump target positions. One of the things to mention here is you are going to need to set an interpolation time. Typically, you would want to match that to your network sync time so that as you're setting these targets, the network can interpolate between them to get precise tight control. This example here, we're going to start off with a cyclic synchronous position with a sine wave using PDOs. So before we run the script, we're going to go over a few different things that are taking place here. So one of the things that's different about this one here is we're setting an interpolation time. This specifically is where it's set. And above this, we also have our network sync time. So setting network sync and setting our interpolation. We also have the similar function where we're generating our points for our sine wave. We're then going to iterate through those points. One thing I want to mention here, I am using this perf counter functionality. The idea is that when you're using traditional time.sleep, it's pausing the execution, while perf counter is going to use your computer's clock to send those. So if you want to run something for 10 seconds, it is much better use for actually running it at 10 seconds. But one thing to mention is it's going to use up a lot more CPU resources to make sure that it's sent at the correct time. Other than that, it's pretty much the same. Every time I'm writing to the process data object, I'm writing to all of the objects at once. So I'm writing the target position and the control word in this loop. And then similar to the other scripts before, we can pause this or stop this at any time by pressing Control C, and it's going to bring us back to the pre-operational state. So we're going to run this script now. Essentially, enable a sine wave. You can see here. This is synchronous position mode is really good for precise position control. That interpolation time really allows you to tighten up the control loop instead of using something like an STO, which it needs to kind of say, hey, can I send this data? The device says, all right, send it. This is essentially the fastest way to control these actuators of position is to use cyclic synchronous position with process data objects and have those mappings set up. So all you need to do from your controller side is get into the cyclic synchronous position mode and start dumping targets.
Okay, thanks so much, Marcel, for that. And now on to the question and answer portion of our event. To participate, click on the Q&A icon in your navigation center, and then just type your question into the available text box before clicking send. If we're unable to answer all our questions, we'll be sure to share them with Marcel, who can reply to you offline. Okay, so let's get going here. Our first question comes from Charles, who wants to know, what is the difference between SDO and PDO communication, and when should I use each?
Yeah, so I think in a general sense, SDOs are a great place to start. You don't have to use any of the existing mappings. You're being very explicit on what data objects you want to access. It's good to kind of send out, hey, for example, sending a control word to get the device into an operation enabled state. Can I send this to the control word, which is 6040? And am I able to read back the status word as well to see if that change had taken place? PDOs are a little more complicated in terms of setup. You have to have the mappings already existing. And one thing to mention is that PDOs will take priority over SDOs in communication. So if you are writing a program that's using both PDOs and SDOs and are accessing the same object, be aware that if they're accessing the same object, there's going to be a condition where it gets into kind of an abnormal state. So it's good to start off with SDOs for kind of, hey, does communication work? Am I seeing the messages in response? And then PDOs once you want to really tighten up the cyclic communication for more real time.
Okay, terrific. Thanks for that. Keep the questions coming. This one comes from Lloyd, who wants to know, what hardware do I need to get started with the FHA mini actuator, and how do I connect everything?
Yeah, so like I mentioned before, you're going to need a CAN to USB adapter. There are many different versions off the shelf. A good example of this is the Peak Orcavaser. But one thing to mention for those embedded type applications, being able to use socket CAN, there's different hats you could use on, say, something like a Raspberry Pi, which allows you to do the same effect. The idea is you have a CAN interface that you're working with, whether that's a USB plugin or something on like a Raspberry Pi where you're putting a hat on. And that's for CAN. You're going to need your termination resistor to make sure the bus is electrically sound. And then you're going to need an actuator. You're going to need power. And you're going to need cables to connect everything together. And typically, it would be good to have a regen clamp to eat up and burn off any of the regeneration, especially for vertical type applications.
Okay, thanks. Keep the questions coming. This one comes from Rachel, who wants to know, how does the actuator change states, and what should I look for in the control and status words?
So a good place to start, if you go to that README page, there's a whole DS402 state machine, and the main secret there is to look at the specific bits. So when you're writing a control word bit to get to a different state, the status word is going to reflect that. And so being able to look at those transitions and see if I go to, say, ready to switch on, does my status word reflect that? And that will help you kind of get to the basic communications, looking at those transitions, seeing what bits are involved, and then also, taking a manual and referencing, are these the correct transitions? Yeah.
Okay, thanks for that. This one from Evan, who asks, what should I do if there's a fault or the actuator isn't working correctly?
So in a general sense, for actually talking to the actuator, you're going to need to have it correctly wired up. You're going to have the bit rate set correctly, and you're going to have unique node IDs. If you plug this in and you say you have two node ones, it's going to be difficult. They're essentially, it's going to confuse. Hey, we have two of these devices on the same node. Messaging is not okay. But once you do have that unique node ID, the status word is going to reflect that. And there's an emergency element where if you do have a network level fault or issue, it's going to be reflected in that emergency message. So if you have, say, a following error fault, the first thing that's going to happen is it's going to trigger that fault. Your status word is going to reflect that fault. And then the status flags object 200D is going to tell you what that is. In regards to troubleshooting it, it's going to then say, okay, so since I have a position window fault or a velocity window fault, I now need to say, am I tracking correctly? I was supposed to be at this target, but I'm not. Is it something in my setup where the window is too tight and I'm not able to achieve that in a certain period of time? Or is it something where I hadn't cleared the following window error, so it's not letting me move to ensure that the system is safe in operation?
And Marcel, thanks so much for that great presentation. And that's all the time we have for questions today. We appreciate your time and expertise on today's topic. And also thanks to our sponsor, Harmonic Drive, as well as to all of you in the audience. We appreciate your attention and participation in the Q&A. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Feel free to share that with your peers and colleagues who may not have been able to join us live today. On behalf of our guest, Marcel Almonte, I'm Michael Krieger. Thanks for joining us and have a great day.